Bismillahirrahmanirrahim. This is 19 and 17 Yasir Zaid, and I'll be taking you through our microcontroller project that was line follower using Arduino breadboard. Then we did some interfacing for each of the sensors, and then we went to the final version of our robot. So we had 6 sensors in front of our robot. If first of all, I am going to take you through the components. This is IR sensors. This is its potentiometer that's used to set its range. It has a range of 5 to 10 centimeters in front, so it just gives 0 and 1. It is a digital form of a sensor. This out pin, VCC ground, and this out pin is used to take our signal. Now coming to the next part, this is our Arduino Mega ATMEGA 2560. The additional benefit it has over UNO is its additional pins. All these pins right here additional. Now why we use 2560? We use 2560 because we had load that was more than what one Arduino could handle, because all these pins were covered by our 293D motor shield, and rest that was left was pretty much less than what we were expecting to use, because we had current sensor, voltage sensor, ultrasonic sensor, tachometer, LCD, and some other things to tackle with, which we tackled right here. Now moving ahead, the operating voltage of this Arduino Mega is 9 volts. This is our voltage sensor. Yes, this is our voltage sensor. Our voltage sensor is basically the voltage divider of 30 kilo ohm resistor and 7 kilo ohm resistor. We pass the voltage from, we give positive and negative here, whatever is to be measured, VCC ground, and this center one is the signal that we use, and we read it. It is an analog type of sensor. It gives us an analog value which we using ADC convert to the value relative to the data table that we get, and then we can just evaluate what's the value of the voltage that we get. This right here is the signal pin, the only pin that goes to Arduino, in our case A8. Now coming to the next, so first of all, I'll be taking you through, these are the separate codes for each type of thing that we are using. So this here is the code to display anything on LCD. We use a library called liquid crystal underscore I2C because we are using an I2C controller. This reduces our pin to SDA and SCL. Instead of using a large number, that is 12 pins of LCD, we use only 2 pins, that is SDA and SCL, and rest of the it is tackled by our this protocol, communication protocol, I2C protocol. Now these are all the commands that we can use with I2C, whether we want our cursor to return to initial position, whether we want cursor to blink or not, whether we want something to be displayed or not, we want our display to scroll or not, we want backlight on off or whatever. Now coming to the next part, this code right here, well, I have got 2 versions of this code. It's for the ultrasonic sensor to detect distance. This is the first code. It uses no libraries and only code to see what's the distance of the obstacle in front from the ultrasonic sensor. So this is the part of code that's responsible without the library. We used it in our C version of the code, but for our code that we used in Arduino IDE, we used this version that had used this library named newping.h. It was capable of measuring distance up to some 400 centimeters. This right here we have written, it can measure more, but still up to 13 feet. Now all we have to do to initiate a ultrasonic register is to give it what is the number of the trigger pin, echo pin, and what is the maximum distance we are going to measure, and this new ping type sonar object is ready, and we can use it to check the distance, because our robot was supposed to go straight and then stop whenever an obstacle comes in front of it. I am explaining all the respective sensors first, and then I'll come to what our robot was supposed to do. So let's stick to what we are doing. So this is encoder or tachometer. This was supposed to count how far our robot has traveled. This code was written by me. So it counts the number of slots, and then because each rotation had 20 slots, then it counted the number of rotations. 20 slot meant one rotation, and then we could just multiply it with the diameter to get our velocity and everything that we wanted, whether it be the distance traveled or other things. Now okay, let's turn the internet off. Okay, now coming to the next part. This is the code for our voltage sensor. Now, as I told, it is an analog type sensor, so we got our input at A0. This is just a sample code that was used to test individual sensors. When we compiled it, we assigned different pin numbers. That's in our block diagram that I'll be showing shortly. And these are the sensors. As I told, 30K and 7K resistors were used as voltage divider in the voltage sensor. So using this formula of R2 over R1 plus R2, we calculated what's our voltage that we gave it. So first ADC conversion, then we convert it to voltage, and then we can just print it on LCD. Now coming to the next part, this is the code for current sensor. It's quite a lengthy code, but making long things short, it's nothing that hard. As I told you, it is a type of analog sensor. We use the analog pin to get our input. It's quite inaccurate sensor, so we get 30 samples and then we take its average to see what's the value. Just to take the average is the better way of getting the values when we are getting many ups and downs. So here is its function. It's nothing, it just converts from ADC to the respective value with respect to what's the sensors, whatever the sensors datasheet tells us, and then seeing the matching values, we just can calculate high peak time, low peak time, and then we can calculate the voltage. But in our case, it's not high or low peak, it's just simple DC current. Now coming to the next part, we were also supposed to record our path that robot traveled in the SD card. So this is the code for writing to SD card in Arduino IDE. So we use a library called spi.h and st.h. We create an object type myfile, then we just initialize it by st.begin, and then we can write to SD card whatever we want to. We open the file, we write to it, and then we close the file. Here it is. We open the file using the myfile type object, and we write to file whatever we want, and then we close the file. So this is the procedure for writing to SD card in Arduino IDE. Similarly, we had another code that was for reading from SD card. So this is the code responsible for reading from SD card. Same, we include both the libraries SPI, st.h. I am just explaining them individually because we tested them individually first and then we compiled them all together. I'll take you to the compiled code afterwards, but first of all I just want to go through whatever work we have done. So this is how we SD card.begin begins the SD card, then we open the SD card, and then we just write to our object, copying everything in our C type string, and then we can just print it to serial monitor, LCD, or we use it for any type of logic to return or whatever. So these are all the sensors and things that we were supposed to use, making our logic a quite bit simple. So now I will be taking you to the block diagram to explain you what we have done so far. So this right here is our block diagram. So what basically our robot is, it's a 2560 microprocessor connected with these 6 IR type sensors. I will rather, so these are 6 IR sensors connected to analog pin 0 to 5, these 6 pins are responsible for our IR sensor logics, and this is our ultrasonic sensor. As I told you, it has 2 pins, echo and trigger, which are connected to 45 and 46 number digital pins. And then we have current sensor, which is the analog type sensor, which is connected to analog 9. Our voltage sensor is connected to analog 8. Our tachometer, which is responsible for counting the number of rotations for the wheel, is connected to pin number 47. Now our SD card has 4 pins: MISO, MOSI, SCK and CS, where SCK and CS are 2 digital pins, but MISO, MOSI are different depending on the version of Arduino you are using. It's written in the data sheet. Now for the motor driver, we used L293D type motor driver. It's just because we had 4-wheeled robot, so 4-wheeled robot uses L293D to control. Now what a 293D motor driver is, it's basically a H-bridge that can operate motor in forward and backwards direction, making it possible for us to maneuver. Now the reason I have not written pins here is because it has some 9 pins, out of which 4 are PWM pins and the 4 are digital pins, and we just couldn't use it right here to control. I couldn't write all those here, but I have mentioned them on my project. Now coming to LCD, because it was connected to I2C, we got only 2 pins, STA and SCL. Again, STA and SCL different for Arduino Uno and Arduino Mega, so I just wrote STA and SCL. Now let's move to the version. Let's move to the compiled version of code, I guess, first, and then I'll be explaining you how we made our PCB. So right here I included all the libraries we will be using. This new ping.h is library responsible for measuring the distance from ultrasonic sensor. afmotor.h is the library responsible for operating L293D motor driver. This liquid crystal underscore I2C is responsible for operating our LCD through STA and SCL. These are all the variables that we will be needing to measure our current, and these are all the values for current and voltage sensor, the resistance values and all that I told earlier. Now these are all the pin numbers that we will be using. The earlier codes had random pin numbers. They were just to test, and here they have been assigned according to what was left and the pins that we are free, of course. So here we initialize 2 types of object: the new ping, which is the ultrasonic object, and a liquid crystal type object. And these are the this is the initialization of 4 motors. The one where 1, 2 is the left side motor and 3, 4 is the right side motor. Now we initialized our LCD. In setup, we declared whatever is input. These are the 6 sensors that are input, and ACS pin, this was for SD card, current sensor. And here we started our Arduino. Now this is just to give an initial push, telling that our robot has started. Now these are the this part right here, which I have commented out, is responsible for serial monitoring. So it was the testing part. It was used to serially communicate to our computer while testing phase, that which sensor is working fine and which is not. So it just printed whichever sensor was on or off. So coming to our conditions that we had, so we basically made 4 conditions in total. We just used OR between the left sensors, between the center sensors, and between the right side sensors. And then basically after doing it, we made the final decisions of what state it was in. Whether it was in current is the variable that stores which is the state. So current is basically state, whether it's state 1, 2, 3 or 4. Now 1, 2, 3, 4 means right, left, straight and stop. So right, left, straight and stop, the T conditions. Now moving to what if our state is 3, our robot is supposed to move straight forward. This is the straight condition for our robot. So it is supposed to go straight up till the time our side sensors don't trigger anything, which means there is no line underneath the robot to move it on the side. So our robot is supposed to move straight on line. If the turn comes, it's supposed to take the sharp turns and store its path, while it's also showing the current value, voltage value, and rest of the things. Now this is the condition for left turn. The motors on the left rotate backwards, and the motors on the right rotate forward. Now coming to the next part, after every condition, this release means stop. This is just to make sure that it is the continuous state machine, and not it does not get stuck or skip the line while running. So now after that, this is the condition to turn right. Our right side motors, which are motor 3 and 4, are turning backwards, and our left side motors are going forward. So whenever the condition, the state for turning left or right is met, the respective condition goes there. Now this is for T junction. So what basically we were supposed to do initially, the way we programmed it, we were going to take a U-turn. So this is the program for U-turn, calculated manually, that how long will it take to go back. Now I wonder if it's the right one. Yes. So this is the current measurement, this is a voltage measurement, current measurement, voltage measurement. After that we have some distance measurement to stop whenever our distance is less than 14 centimeters, and then we displayed everything on LCD. This is the sample code to print to LCD. Now this is all for our robot. Our robot basically found out which condition was necessary, and when that condition was met, it turned right, left went straight, turned back, or read its path. Now taking you to the versions of our robot that we have been making. So first of all, I will take you through the PCB version of robot, because that was the most difficult part. Now right here, because we had no footprints for many of our components, as was for 293D, for current sensor, voltage sensor, and many other things. So the first thing that we did was we designed a footprint for the robot. This is the footprint of Arduino Mega. These are all the connectors of Arduino. We named them with respect to what they are named, as they are named on Arduino. Then this portion right here, this portion right here, this is the Arduino Mega part. Everything related to Arduino Mega is attached here, and these things right here, these are our IR sensors. Every IR sensor has 3 legs, VCC, ground, and an analog pin. So, and this one right here is our ultrasonic sensor connector. This one right here is our jump. It's the PCB jump that we used to move to the other part of the second part of the PCB, because our PCB was in 2 pieces. So this is this is a footprint for, this is the connector for current sensor, this is the connector for voltage sensor, this right here is the connector for these all right here, these are our connector for, this is the footprint of basically 293D. You can think of it like that. Means these are for motors, these are to connect motors, and this right here is for 293D. This part right here is to connect to the LCD. This part is to connect IMU. It was necessary to create it because we had another project that was related to path planning of mobile robots, so we had to use IMU compass in it. And this right here is for our tachometer, which is our sort of IR sensor, but it's used to count the distance. Now Coming to the PCB part, so I'll take you through this whole portion right here. This portion right here, it had to be designed because it was a 3D and it had no footprint, so just it was custom designed by taking measurements through scales, and then we just made its footprint right here. And zooming out a bit, this is the jumper that I used. I just named the pins same as was necessary. I named it 1 and 1 and made the respective distance, and then I etched it on PCB and used it. This is another part. This was made to attach our resistor array of 10 kilo ohm that was necessary to guide stray voltage of the IR sensors. Now this jumper is used right here. You can see right here, this is the jump. The function how it helps us in making PCB is because this is 1 and this is 1, and while designing the component I have mentioned the pins the same number, so it just won't interrupt and you don't have to attach things like that. It's basically the jumper wires, but it's technically a part of an third part edge for the PCB. So because this is 1 and this is 1, so they are connected to the same part, so the software won't bother. It's just an easy way to get through the tricky PCBs that don't let you make the path that clear. Now these are all 10 pins connected here, these are 10 pins connected here. This is for ultrasonic sensor, these 4 pins, and these are IR sensor. These are for IR sensor 1, 2. These are for IR sensor 1, 2, 3, 4, and 5 and 6. These are for IR sensors. These are the connectors for these right here. These right here are the connectors for LCD and IMU. The pinouts have been mentioned in schematics, so it's just easier to make PCB here. Now all these red pins, these are the leftover jumpers that we could not tackle, so we had to connect a wire out of PCB physically, so because it was a single layer PCB. And some other things that were designed were this footprint of voltage sensor. It had to be designed because it was not there, so it's the first one made. And this is the footprint of current sensor, same, quite similar, but it was custom designed because it was not here. So everything was placed here on the PCB. Another thing that I have to mention is we modified our current sensor, voltage sensor, and the 293D motor driver because it had the female pins connected to it. So we just removed those female pins and connected the male pins instead and used them to mount it right here, which was also a quite hectic part, removing those, desoldering all those pins and then soldering them back. Now the next part, where should we move to for the next part? So these you can see in the components, if I can show you these our components. Where is our custom designed components? These are all the components that were designed. For example, this is the voltage sensor, which I can place right here, and this is the current sensor, which I can place right here. These are Arduino cells that were connected. This jump of 10 was custom designed, it's right here. And then okay, and all these components you can see right here are custom designed, and it took quite a lot of time. So now, as we have went through all this and the other part, now moving back to our final report. So this is the same circuit I have told you already in detail. This is the PCB PDF that was used to print the PCB onto the copper layer. Hope if I have that, it's somewhere micro PCB. So our PCB went through many versions, you can see right here, and then we got our final version, which was version 5, which is the version in that diagram, this right here. Okay, this is our final PCB. This is for 293D, this is for Arduino, all the relative sensors, our power, and everything was on board on the system. Now taking you further in our report, this is the PCB I already explained in detail, and after that this is our robot. I'll add a better picture instead of these. Now this is the first version of our robot. This is how we attached the sensors initially. Another thing to mention is that we attached tapes on these black LEDs so that they don't interfere with the one neighboring them. Now, so anything that I have not mentioned yet? Nope, nothing. So coming to the conclusion of our robot, I wonder if we have some PCB form pictures that we have got the proof of our work. So this was the initial track that we designed on page to plan for our robot, that where it's supposed to go and how are we supposed to make the alignment for our sensors. And after that